Let's take a look at some of the core concepts in concurrency by using a busy restaurant kitchen as an example. There's four key concepts here. First up, we have parallelism versus concurrency. Second, synchronization primitives. Third, message passing. And fourth, race conditions. So if we take a look at the first one here, parallelism versus concurrency, let's take how a multiple cook scenario could really increase the parallelism versus a single cook that is multitasking between different dishes. This would be concurrency. So, in the parallelism example here, each of the cooks could really make one part of the meal. So, one could cook a steak, one could cook mashed potatoes, another one could cook a salad. And once they prepare that meal together, that's the finished level of parallelism. With concurrency here, with a cook, the same cook would potentially put a steak on the grill, go ahead and stir up some mashed potatoes, and then start to chop up the salad. And so that one cook could be highly utilized for that specific meal. In the other scenario, with the multiple cooks, each of the cooks actually could be preparing several different steak dishes at the same time. So really, there are two different concepts when you're thinking about parallelism versus concurrency. Next up, we have synchronization primitives. And a good way to describe this would be a ticket dispenser that makes a customer line up and take a number in order to be served. And this would avoid making a bunch of crowding at the counter and would even limit the amount of people that would actually go into the dining room. What happens here is that the tickets dispenser is the synchronization. So each of the customers gets a ticket, and they're only called when there's room in the dinner area for people to sit, and also when the cashier is actually available, then you're able to actually order the food. So this is really similar to many other types of concurrency problems in the real world, in that you would maybe put work inside of a queue, and each of the threads would actually grab one of the items at a time, and then that queue is actually the thing that's locking things up. In terms of message passing, this is also a core concept in concurrency, is that there are different stations, but maybe there is a grill, as a fryer, there's the salad section, and these are loosely coupled, right? So they're not really working together, but they do communicate, because when they're done, they put the thing that they've produced onto the counter, and then go ahead and the waiter will come by and pick up each of those separate items. So really, this is the counter is a form of message passing. So once you know that there's something on the counter, you know that that particular job is done, but they don't necessarily even need to communicate with each other than to grab the order initially. Likewise, a race condition is something that does happen and has to be protected against. And one of the things that could come up is there's two customers that order at the same time. If you're lazy, you just always, assume that, that because you put your order in at the same time as another waiter in the restaurant, that as soon as the food is out, you just give it to the customer. But in the situation where there's two customers that simultaneously order, there could actually be a race condition where the waiter could bring the wrong food to the wrong customer. And this does actually happen in the real world. So the concept here is that you do have to protect against race conditions by maybe using synchronization or message passing or some other technique to avoid those kind of interactions. So really, multiple cooks show parallelism. A ticket dispenser would enforce or order synchronization. Passing orders between stations would demonstrate message passing. And then finally, customers would have potentially concurrency risks if there's mixed up orders with race conditions. So you can see these situations come up quite a bit in programming, and that's why languages like Rust are so powerful, because they prevent some of these things from happening more easily. And this is what I think we're going to see with modern compiled languages. Here we have a dining philosopher problem. What's interesting about this problem is that you need to figure out a way for a bunch of people sitting at a table, in this case, philosophers, to all figure out a way to share a certain amount of forks. And what's interesting about this particular issue is that it can expose certain problems like deadlocks, for example. And one of the things that you can do to prevent this is to use the correct forms of concurrency. So in this case, the mutex is going to provide exclusive fork access. So these are eating forks. The arc allows sharing forks between philosophers. So the simulation is going to print the start time, the eating duration, and the total time for all the philosophers, and also the total time approximately equals the philosophers divided by the forks. So that's the number that can eat concurrently. So when you're doing a form of simulation on concurrency, it's always really important to benchmark it to make sure that what you think is happening is happening. So if you introduce a bunch of threads and nothing speeds up, then there could be a problem. So in this case, we're going to use these techniques, which is a mutex to represent exclusive fork access. We're also going to wrap it in an arc to share mutexes between threads. We're also going to use a numbered philosopher and acquire a lower fork first. And then finally, we're going to do all the timing for the simulation. So again, really critical to print out the time speed up. There is a diminishing return that's going to happen with concurrency, and this is called Amdahl's law, where the more there is something that's going to weight, there's diminishing returns with the concurrency. So you need to double check that it's even worth it to actually make something multi-threaded. So in this situation here, we're going to use the standard library. This is arc, mutex, thread, duration. We're going to implement a fork. So in this case, this is the thing that the philosophers are going to use. And then we're going to implement a philosopher. And then right here, we have the philosopher. We make it an instance of it. And then we have an eat method here, where in this case, it shows the logic behind the fact that they need to pick up the forks in a way that really prevents deadlocks. But we do have some debugging information, which also is really helpful when you're first, going through and building out concurrent code, is to have the really the printing or the logging statements. Logging is even better, so that you know exactly what's happening. In fact, if you had a log.debug, you could debug it while you're developing it, and then not show those messages when it's in production. But then if there's an issue and you need to do some more development, you would toggle on the debug method. So here we have the main method, and this main method is going to show that we only have 4 forks at the table, and this is going to print out the information about it. And then we're going to apply mutex around this so that it's going to prevent issues with shared access to a fork, which would cause massive problems like a deadlock. And here we see all the philosophers. There's a vector right here that it is a section that includes everybody that we want to have at the table. And then here we're going to put this into our collection. Finally, we're going to spawn threads here so that everybody can start eating together. And then finally, we're going to go ahead and print everything together. So really the key takeaway here is that the mutex is what is helpful so that we can have everybody try to eat, but there's some logic around who can get the fork at a given time. So let's go ahead and run this. And if we want to go into Dining Philosopher here, and we type in cargo run, we can see the simulation. So this is, again, critical when you're doing multi-threaded programming, is to go ahead and build out the instrumentation for what exactly is happening, because the philosophers, for example, need to be able to pick up both forks, right? So we're debugging that. And we also have the ability to print out the messages when they're done, when they started, and at the very end. Again, you should benchmark it and say, well, how many philosophers were there? Well, we have approximately, we can see actually from Rust, it'll tell us exactly the list of philosophers here. And then we look at the time, and we should have a level of efficiency because of the fact that we're able to use multi-threaded programming to, speed up the work. So in a nutshell, this is a great way to play around with some of the classic problems in concurrency by using the Rust language. Rust has a lot of safety techniques as well that will prevent you from compiling code with known errors. It's not going to prevent every error, but this is a great idea for maybe a future level of concurrency that you could use in a real world project. Here we have a great example of how to use threads to speed up parallel fetch on the web. First up, we use Wikipedia here to fetch pages, and then I process each of the page's content. So the text inside of the Wikipedia page. I also collect timing metrics to ensure that I'm actually doing things that I expect to be doing. And then over here, I have concurrent page processing, and this is where all the work happens. And then finally, we're able to show how you can use a external tool. In this case, this is Rayon and Wikipedia to do a lot of the heavy lifting for us. So let's go ahead and take a look at this cargo file here. You can see Wikipedia, you can see Rayon here, and if we pull into this particular example, you can see Rayon, Wikipedia, Wikipedia page, etc. This is where I've been able to leverage the libraries that do all the heavy lifting for me. In the case of Rayon, what's nice about it is it intelligently will launch threads in a way that allows me to leverage it to do the parallelization for me. Here I have a process page, and then I also have a const here, which includes several NBA players, in fact, 9 NBA players. And in this particular example, here I have the process page. So I have a function here that's able to get the page and the content. Now that I've got all that, all we have to do to leverage the concurrency of Rayon is to use par.iter. So in the case of regular concurrency, you would do .iter, which would just be without threads. In this case, though, I'm launching a thread per operation here to fetch those pages. Also, I go through here and then I process the page as well. So I can do the same thing as well. I can actually go through here and I can say, look again, par.iter, and we can actually see this when I hover over it. It says convert self into a parallel iterator, uses Rayon Prelude. So what's nice about this is it's able to process in a thread everything that's happening in the page, as well as give me some descriptive statistics. Finally, at the very end here, I'm able to print a bunch of different metrics. So how long did it take to process a page? Also, what is the average time per page? And then finally, what are the total number of pages that were processed? And then this is also a nice metric to verify that you are, in fact, using concurrency, is what were the number of threads that were actually used. So now that we've got all that going, let's go ahead and run it. And you can see here, extremely quick, right? It was able to process 9 different Wikipedia pages, and almost like it was instantaneous. And we can see here that, in fact, we're able to grab a sentence from the first Michael Jordan page. We're able to grab a sentence from this other page, and we can see that, in fact, the page time, the total time, the average time, total number of pages, all of these give us great descriptive statistics on how to benchmark whether this is a good formula for us to use or not. And again, this is really one of the most important parts of multi-threaded programming, is to actually benchmark it so you know that you're improving things, not slowing things down or causing unneeded complexity.